Hey everybody, my name is Matthew Gunton. I'm going to be going through the Triton Puzzles today. So this is a great way for people to get a good intuition for Triton. One of the reasons I really like this specific problem set is that it gives you a visualizer, which makes it a lot easier to understand the indexing and especially the masking concept when it comes to Triton. So without further ado, let's just dive right in here. I've gone ahead and installed our dependencies. Generally, the way that this is going to work is I'm going to read for you the puzzle, what they want us to do. I'd recommend that you pause the video, go through, try to figure it out yourself, and then come back for the explanation of how it works. So let's go ahead and make sure that everything is working for our dependencies. There we go. Awesome. So to explain the visualizer here, the really great thing about this is you can see how changing the program ID changes which parts of the source data we're reading from. In my opinion, it's just instantly intuitive. I think it's one of the most important ways to teach this. So let's dive in. Puzzle number 1. In this case, they want us to add a constant to the vector. We're going to use one program ID axis. We're going to be given block size B0, and we're told that B0 is always the full length of X. We don't have to worry about varying here. So let's dive in. In PyTorch, we write this as X plus 10. Very simple. With Triton, we have the concept of loading and storing that we have to go into here. So you can see what's already been written is the input data X, which is tl.load X pointer plus range. So the first question you're going to have is, well, what is range? In Triton, this is a low-level language. So we're dealing with a pointer. If you've done low-level stuff before, this is going to make a lot of sense to you. We're starting, let's say we have an array of size 5. The first element is the address, just plus 0. The second element is the address of the first one, plus 1. Then this one would be the address of the first one, plus 2, etc., etc. This is known as pointer arithmetic. And so because Triton, we are dealing with tensors, and generally we want our program to be easily parallelizable, we pass through this range, which gives us all of the values from 0 to whatever our batch size is. So in this case, X is going to be all of the values that are inside of X, because we know that B0 is equal to N0, which is the length of X. Now, the next thing that we want to do is our actual operation. So I'm going to say Z equals X plus 10, and just like that, that's the operation. Nothing more, nothing less. Now, the last thing that we have to do is actually take this in the kernel and write it to memory so that we can use it. So you'll notice here Z pointer is also one of the parameters, and we are going to write to Z pointer for the entire range that we read from X. So the intuition here is that X, we're pulling in all of this data range, we're adding 10, and then we're writing the results for the exact same original data range. After we've set where we're writing, the next question is, well, what are we writing? In this case, Z. Finally, we have mask, and this is probably the most important concept in Triton, as it's what's going to be very helpful when we're writing these things for batches. So a mask is basically a way for Triton to communicate to CUDA that there's only some amount of this data that I care about. So as a nice visual, let's come back to our array here, 0, 1, 2, 3, 4. If I want all of these values, I'd have a mask where everything is true. And I would just write here, mask true. then absolutely everything in this range is going to be read from. But the truth is, we don't really want everything to always be true, because there are situations where our range may be more than we actually want. So, for example, let's say that our range was, let's say we made a mistake. B0 is actually larger than N0. If that's the case, like here, I'm just going to pick letters as garbage values. This would give us the wrong calculation because we're using the wrong data. So what we would do is we'd want the mask to say, ignore everything that might be outside of the N0. And so the way that we'd write that is we'd say, if range, pardon me, not if, give me everything where range is less than N0. And I'll call this X range so that it's a little bit nicer for IDE. As you remember, X range is just this array. It's akin to the PyTorch A range, where we're going from 0 to wherever we set the endpoint to, in this case, B0. So you can see here, those results match exactly as expected, and then bam, they work. Now, to showcase why this visualizer is useful, let's say that I wanted to really only get half of the data in the range. So I adjust my mask to be X is less than NO divided by 2. They, of course, aren't going to match. But in the visualizer, you can see that while for the load, where there is no mask, we pull absolutely everything, for store, we're only getting half. And that's the key point. This is what allows us to be more precise with our data. There's a puzzle further down where we're going to be pushed to use mask to make sure we're not reading too little data. The important thing to remember is that mask exists so that we have this precision, and the reason that we need to have that precision is because Triton requires that your TL.arrange always be given powers of 2. So if our batch size was something unhappy, I'll pick 200 because it'll come up later. 200 is unhappy. And so we would have to find another way. For example, the next closest power of 2 is 256. We don't want to read an extra 56 elements. Mask is how we're going to do it. So we went pretty deep into this one. It's because I really care about building an intuition here for you. So I'll go ahead and set this to be correct again. They match. Let's move on. Puzzle number 2. So now we're going to be adding a constant to a vector. We're going to use one program block axis. And it's important to note that B0 is now not equal to N0. So we're finally having to process this in chunks. And so this is going to be the beginning of PID. So when we do GPU programming, we generally have grid and thread blocks as a way to divide up work for CUDA. If you're interested in this, there's a lot of great courses on this. I highly recommend Elliot Aldridge's course about this. It's on Free Code Camp. But the point of bringing this up is to say that we, in Triton, also divide up work. And we write one kernel, which is going to run simultaneously in multiple different places. The way that we divide the work so that each kernel has its own subset is with these grid dimensions. And Triton's version is to call these program IDs. So just like you have a grid dimensions in CUDA where you have X, Y, and Z, for Triton, we have program ID 0, program ID 1, and program ID 2. No more, just those 3. So if we want to make sure we're only focusing on the most important stuff, program ID is how we're going to split up the work so that these kernels running in parallel all have a unique data set that they can work off of. So now that we've defined this, the next thing that we have to figure out is, well, what data do we load? So if you remember from before, we had a X range, which was our TL, Triton language, A range, 0 to B0. And that was it. That was good. That was basically us being able to get everything that we needed. But now that the total length of the stuff we want to operate on, N0, is bigger than B0, we actually need the process ID to be going through different elements here. So for us, that means that we're taking an array that, let's just say it was 0, 1, 2, 3, 4. And now let's say that we have 3 of these, right? I don't want all of them to get the same index of the data. That would be redundant and we would miss some of the stuff we need. So let's say that we have a vector of size 12, right? That would mean that we really want an range that goes from 0 to 11. Well, you can see here that if I add the PID, which is an integer, times the batch size. So in this case, I'll make this easy. PID is equal to 1. This is what it will look like. We get PID 0 times, let's just make this clean and match it with 4, right? So anything times 0 is going to be 0. So this is plus 0. This is plus 4, right? 1 times 4. So 4, 5, 6, 7. This is going to be plus 8. So this is going to be 8, 9, 10, 11. And so that perfectly divides up the work. So this is going to be the algorithm that we're going to use to determine what range of indexes each kernel should run on based on its program ID. Once this is set up, the next part is to load in the data. So we're going to again do a tl.load, and we're going to again do xPointer plus xRange. In this case, I'm going to add a mask to load, just basically to be for good form. So the mask here is going to be, well, xRange is less than n0. So if we come back to that example that I had before, let's say that there was some mistake in the dispatching and I had an extra process ID. Right. In our example here, N0 is equal to 12, right? B0 is equal to 4. This will keep writing, and it will actually read bad data, right? Our data actually ends here, so this whole kernel shouldn't have anything. The point of our mask, which I'll bring back here, I'll just have to rewrite it. The point of the mask that we have is to be able to show that we will ignore that because, as you saw, the X range will have values that are greater than N0. Therefore, we won't have to worry. It will ignore it, even though the dispatching was wrong. So, now that that's set, we can do X plus 10, Z equals Z. And then we have the same output as well. So the key idea that's being expressed here is that dividing up the work using this type of addition, where we take the A range and add it PID times the batch size, should be an efficient way to split up the work. So let's go ahead and see if I didn't make any mistakes. Oh, yes. I forgot to add in Z. It won't match because I had the Z pointer, and then there we go. That matches exactly. Now, this is where the visualizer kind of helps us build intuition, right? Program ID 0 is what varies here. There's 6 of them. And so as I switch, you can see that the amount of, the place in the source tensor that I'm reading from adjusts. I guess I should say properly source vector. And likewise, the place that I'm writing to in the output accordingly changes. So it's useful to see here that when I come to the end, there we go. That mask is actually very important because it stops us from reading garbage. So you can see here we have more than enough stuff set aside, right? Size B0, but it's no longer useful, so we're going to ignore it. Moving on now to puzzle 3. This is an outer vector add. This is where we're going to be dealing with broadcasting more explicitly, and then also we're going to be talking about striding in more detail. So the problem is we have 2 vectors, x and y, and we want to add them together element-wise. Our block size is going to be the same length as vector x, and b1 is going to be the same as vector y. The key thing to note is that we're doing a broadcast here. We're not just doing element-wise addition like we were here. Instead, we're going to be expanding the final output to be of shape y, which is b1, x, which is b0. So that means if I write this out, you have 1 by n0 plus n1 by 1, which will give us n1 by n0. So let's dive into the Triton here. We're going to use a program ID for good measure, but note that the block size is always the same as the vector length x, n0. So strictly speaking, you don't need to have the program ID. This will run in one go. Next thing we need to do is read in our data. So we have x arrange. We're going to have it to be size b0. And then, just like we did before, for good measure, we're going to have this be adjusted so that it varies with program ID. Now, there's one thing that we're going to need to change from before, which is specifically our shape. So I'm going to write this out. You can see here it's identical to what we had before. We're making sure that we're reading from our batch range, and then we're masking so that anything that might be outside of the happy range for x is masked out. Our change, though, is that we need to tell Triton what the shape of this data is. The way this is written right now, being identical to the way it was written up here, tells Triton that this is a one-dimensional one-dimensional tensor, B0. The problem is we're going to be doing a broadcast, and so we really want it to be read as 1 by B0. So to communicate that to Triton, I'm going to use the same notation here to effectively do an unsqueeze, right? None, and then the colon. This is going to be critical in telling Triton to expect that the shape is 2D. Let me continue here. We'll adjust Y range so that it is correctly done. Y is of the reverse shape, right? It's not 1 by B0. It's actually B1 by 1. So I adjust this notation here, and then when I load, I make sure I'm reading from Y pointer in Y range. Remember, it's not guaranteed that X and Y are the same length, so we're going to have separate variables to keep track of them, regardless of broadcasting. So with those two in place, now we can do our addition. So I'm going to write this as Y plus X, because at least for me, it's useful to keep the shape straight in my head. This is N1 by 1 plus N0 by 1, 1 by N0. And so putting these two together, I get N1 by N0, just like we expect. Now, similar to before, we're going to do a store operation. We take our z pointer, we add some kind of range to it, and then we store z, and I'm going to do a mask. Now, this is a little different than what we had done before. Before we had a z that looked identical to x. So we could reuse the range, and the mask was basically identical. In this example, z is actually fundamentally different from the inputs. It's looking like it has a different shape. So what we need to do is build a range that will properly store the elements at the correct addresses. So in order to do this, we have to be aware of striding. So generally in tensors, we will have them written in row major order, meaning that if we have a tensor, let's say it looks like this, in contiguous memory, this would be written as this. And so if I were to be given something like coordinates 1, 1, in our matrix here, we go over 1, down 1, 6. The way that I would get that from contiguous memory is I would need to know the striding. So in this case, we have a matrix of size 2 by 4, right? 2 rows, 4 columns. And so my striding is going to be 4 by 1. And so with this information, what I can do is I'm going to multiply the row by 4, and I'm going to add that with the column by 1. And this will give me 4 plus 1, which equals element number 5. And this will give me, remember it's 0 at the beginning. 0, 1, 2, 3, 4, 5. That will give me the correct value of 6. So all of this is to motivate that when we're building the z range, we need to give it this formula here so that it's able to write to the correct parts of memory. So for us, we have shape n1 by n0, and this means that our striding is going to be n0, 1. So I have my y range. My y is the row. Y range is going to be times n0. And then I'm going to add x range. And this should give me the correct striding pattern so that no matter where we are in our program ID, we're writing to the correct output. Now, the mask is quite simple for this 2D. We have x range needs to be less than n0, and y range needs to be less than n1. So let's see. Awesome. That is correct. And as if you remember, block size is the same size as the total length. We're going to have just one program ID. You can see here we're successfully reading from a 1D, 1D, and then we're outputting it successfully to a 2D matrix. Our results match, and we get the nice puppies. So this is going to be where we start to take program ID very seriously. We're again having two vectors added together with the broadcast we went over. But this time, our block size is always less than the full length, which means that we're always going to need to be batching. And critically, this means that we're going to have to keep track of where we are for both. So if we scroll up to puzzle number 3, we'll see that I actually got extremely lucky here, because if we were to have B0 be significantly smaller, or just frankly smaller than N0, and likewise for B1, you can see that we're only varying on 1 degree of freedom. We have PID, and they're going to stay in lockstep for each. The problem is that when this happens, you can have stuff get out of order. So let me illustrate that by just copying this code and bringing it down here. So if I run this, it will not match. And what we'll basically see is that we move in lockstep for each, which is a problem for our broadcasting because we really need to be able to have these different pieces added together with their corresponding parts. So the way that we fix that is by having our PID vary in two different ways. So you remember from before, we're coming back to the CUDA grid, we had initially X, Y, and Z. We've only been using X with program ID 0. We now need to use Y. So we're going to have program ID 1. So the code is very, very similar to before. X range, we're going to arbitrarily decide that one gets PID 0. And then Y range, again, arbitrarily gets PID 1. And this will ensure that both of them can vary independently of each other. And that will let us have the correct answer. You can see it's literally that simple between the two of them. And in the visualizer here, it should be clear as to why that worked. This one needs to stay the same so that we can do the correct additions. This one will successfully go all the way to the end, and this one will separately be able to move down. So effectively what we were doing before was making it so that we could only get these top parts, right? It was effectively just going through the diagonal. Now it's able to get every single part of the corresponding matrix. So that was a freebie, right? That was fairly straightforward.